Good day, my name is Abella and this is Engineering 211, Mechanics of Deformable Bodies. This presentation is about understanding torsion in engineering mechanics, and we will be having an introduction to torsions, general torsion equations, and its applications and examples. First up, introduction to torsions. What is torsion? Torsion is the mechanical behavior of a structural element, like a shaft or rod, when it is subjected to a twisting action or torque about its longitudinal axis. This twisting leads to shear stress inside the material, angular deformation twisting, and called the angle of twist. And what causes torsions? Torsion occurs when a moment or torque is applied perpendicular to the longitudinal axis of a component. This is common in rotating machinery shafts, example drive shaft or crankshafts, torsion bars in suspension systems, springs and helical rods, fasteners under torque. The general torsion equations are T all over J is equal to the symbol of tau all over R is equal to G times theta all over length or L, where the symbols represents T is the applied torque, symbol J, polar moment of inertia, indicates shaft's resistance to torsions, and symbol tau, shear stress, varies linearly from center to surface, and R is the radius, it will be in meter, and G is equal to the shear modulus, material property relating stress to strain in shear, and the symbol theta, angle of twist in radians, this is measure how much the shaft twists, and the letter L, which represent length of the shaft, and its units is in meter. The applications of general torsion equations in mechanical systems. It is used in analyzing shafts that transmit torques in machines, like motors, turbines, and gearboxes. It ensures that shafts are capable of handling rotational forces without failure. Its application in structural engineering. It helps calculate torsional resistance in beams and other structural components subjected to twisting forces. It ensures stability and safety of structures under dynamic loads. And its applications to material testings. It assists in determining materials properties, such as ultimate shear stress, through experimental setups. Important for selecting materials suitable for high torque applications. And lastly, its application to aerospace and automotive designs. It's applied in designing axles and other components of vehicles, ensuring durability under rotational motor. Crucial for lightweight and high-strength design and aerospace components. Now we will have discuss a problem with finding shear stress. Problem 1 states that a solid circular shaft of diameter 80 mm is subjected to a torque of 1,500 Newton meter. Calculate the maximum shear stress in the shaft. We have the given D is equal to 80 meter, but here in the equations you required radius in meter. So the diameter 80 millimeter will be equal to the radius is equal to 0.04 meter, and the torque is 1,500 Newton meter. The general torsion equations. Torque all over J is equal to shear stress all over radius or equal to G theta all over L. Used in steps, use the polar moment of inertia for solid shafts. J is equal to pi r raised to the fourth power all over 2. It will give us the polar moment of inertia, will give us 4.02 times 10 raised to negative 7 m raised to 4. Now calculate the shear stress. With the given general torsion equation, it will come out shear stress is equal to torque times the radius, all over J. Upon calculations, it will give us a 149.25 megapascal. Problem number 2, angle of twist in hollow shaft. A 3-meter long aluminum hollow shaft with an outer diameter of 60 mm and an inner diameter of 40 mm is subjected to a torque of 600 Newton meter. The shear modulus G for the aluminum is 27 gigapascal. Determine the angle of twist in degrees. We have the given, the length is equal to 3 meter, the diameter, outer diameter is equal to 60 millimeter, and we need the radius. The radius will be 0.03 in meter, and the inner diameter is equal to 40 millimeter, and radius is equal to 0.02 meter, and the torque is 600 Newton meter. The shear modulus of the aluminum is equal to 27 GPa or gigapascal. That would be 27 times 9 raised to 9 power pascal. Again, the general torsion equations. First off, we will calculate the polar moment of inertia, J, and J is equal to phi over 2 times R outer radius raised to the fourth power minus inner radius raised to the fourth power. It will give us 1.02 times 10 raised to negative 7 power m raised to the fourth. Use the torsion equation to find theta. Theta is equal to the torque times length all over shear modulus and J, moment of inertia. It will give us 0.653 radians. Now, converting it into degrees is equal to 0.653 radians times 180 all over pi. It will give us approximately of 37.4 degrees. Problem number 3, in finding the angle of twist in a solid shaft. A solid steel shaft, 1.5 meter long and 30 millimeter in diameter, is subjected to a torque of 800 Newton meter. Determine the angle of twist in degrees. And given also is the shear modulus of steel is 79 gigapascal. Given again, length is equal to 1.5 meter, diameter is 30 millimeter. Again, we need the radius. Radius is equal to 0.015 meter. Torque is equal to Newton meter, and the shear modulus is 79 times 10 raised to the 9th power pascal. The general torsion equations. And first up again, we will calculate the polar moment of inertia. That would be J is equal to pi r raised to the fourth power all over 2. And it will give us the answers by substituting all the known values. 3.98 times 10 raised to the negative 9th power meter to the fourth. Use the torsion equation to find the theta, or the angle of twist. Theta is equal to torque times length all over J, or the shear modulus times the polar moment of inertia. Substituting the known values, we will come up 0.379 radians, and converting to degrees, it will give us to 21.7 degrees. Now that would be all. This is Abella again, and this is Engineering 211 Mechanics of Deformable Bodies. Thank you and have a good day.